This is the second part of lecture 2.2b. We're going to do some examples. So we just talked about the definition of a vertical asymptote, and we saw that it was related to a certain type of limit at infinity. And you should have just written down these three functions, and you need to memorize that these three functions all have vertical asymptotes. And the good news is if you can remember these three, you've basically got your bases covered. You're probably going to recognize most other functions that have vertical asymptotes because they're really kind of variations on these. Let's start with a little check to see if you understood. You have three functions right here, a, b, and c. Which one of these have a vertical asymptote? Great, so you just saw that b and c both have vertical asymptotes. You should have done this without a calculator, hopefully, and just all you need to do is recognize that this function is related to that first one that you're memorizing. It's a reciprocal, it has an x on the bottom. And this is a natural logarithm function. These two have vertical asymptotes, polynomials don't. So in addition to recognizing just basically what kinds of functions have or don't have vertical asymptotes, you should also be able to recognize the limit notation and what it tells you about vertical asymptotes. So try this one. If I tell you that the limit as x approaches infinity of f of x is 6, the limit as x approaches 3 of g of x is 2, and the limit as x approaches 0 of h of x is infinity, which of these three functions has a vertical asymptote? Okay, this one might be a little trickier because you have to process the difference in the notations. What you probably just saw is that the answer is that only h has a vertical asymptote. Notice that these three limits basically represent the three different possibilities we've looked at so far. This one has x going to infinity and the limit equaling a number. This one has x going to a number and the limit equaling a number. And this one has x going to a number and equaling infinity. This is where it's essential that you can keep track of what's your input, what's your output. A vertical asymptote, think about the picture, is when your output is infinity and your input's a number. That's this one right here. That's a vertical asymptote. Now, a horizontal asymptote, if we talked about this, is where your input goes to negative infinity or positive infinity, and your output's a number value for y. But vertical asymptote is when your input's a number and your output is positive or negative infinity. This is pretty important, so let's try one more. Pause if you need to think about this one, and then try this. Awesome. So using the same logic, vertical asymptotes happen when you have inputs that are numbers, but your output turns into positive or negative infinity. So both g and h. This one right here, this is talking about a horizontal asymptote. We're talking about x going to negative infinity, that's the left side of your graph, and the y value staying constant. Okay, after this quick review, let's do some examples. There are a couple different ways I could test this information, but oftentimes I'm just going to give you a function, and I'm going to ask you to identify the vertical asymptotes and then describe the behavior to the right and the left. When you see this second sentence, which is going to be all over your problem set, it's a cue to you that really what I want you to do is write two limits, a right-hand limit and a left-hand limit. Okay, so here's what you do. First, a quick reminder from Algebra 2. If you plug in a number for a function and you get 0 on top and some number on the bottom, way back in Algebra 2, we learned to identify this as a 0, and you think about it on your graph as a point where your function crosses the x-axis, an x-intercept, if you will. When we have these rational functions and we plug in some number, if we get a 0 on the top and the bottom, this actually is no longer a 0. Usually we call this a hole, and graphically, of course, you know that usually that means it looks like this. Sometimes holes can be a little mysterious, so I'm going to put a question mark there just to indicate that you can't always be sure that it's a hole. But for now, that's enough of an idea. And then the important thing to remember is when you have a number that you plug in for the function and your answer comes out to be a number on top and a 0 on the bottom, which you know doesn't exist, graphically what happens is an asymptote. And in particular, a vertical asymptote, although at the time we probably didn't really specify. but this is going to create something that goes up to infinity or down to negative infinity. So in other words, vertical asymptotes happen when the bottom of a function gets close to 0. Okay, so we're going to use this fact to find the vertical asymptotes of this function and then to explain the behavior. We just talked about how to find a vertical asymptote, and so the way that you can use that rule is to say, well, vertical asymptotes happen when the bottom of the function equals 0. And so if I take the bottom of this function, x squared, and I set it equal to 0, I would realize that the vertical asymptote is at x equals 0, and I get that just by solving for x. Obviously, for this example, you probably could have done that in your head, but if you get something more complicated, just use this trick. Now that I know that the vertical asymptote is at x equals 0, please make sure that you do write it as x equals, because this is technically the equation for a vertical line. Now I'm supposed to describe the behavior of this function on the right and the left. And basically what that means is we're going to write limits. If I want to talk about what's happening to this function on the right of 0, I'm going to use the right-hand limit. The limit as x approaches this asymptote 0 from the right, and we're talking about the function x squared minus 4 over x squared. If you used the instinct ideas that we talked about in class today, when we plug very small positive numbers into the top and the bottom, x squared on both the top and the bottom are going to turn into really small positive decimals. And so we're going to have something like -4 over a very small decimal. So my instinct is that this is probably going to equal a negative infinity. Now, unfortunately, instincts aren't the same thing as proof, so here's how you can prove it. Well, first of all, just observe that obviously we can't plug in 0, because we would have a 0 on the bottom of the fraction, which isn't allowed. So what I can do is I can algebraically rewrite this limit, and this is just like what we were doing last week. And I'm going to write it as the limit of x squared over x squared minus 4 over x squared. And that's just an algebraic step that I can take. Now, I know that the limit as x approaches 0 of this is defined because x squared over x squared is really just 1. And I still haven't plugged anything in. I'm just algebraically manipulating this. And since this limit is defined, this whole limit is going to be something like 1 minus, and this limit right here is negative infinity. Observe that as we plug really small decimals in here, this value on the bottom is going to become very, very small, which means the limit is going to become large. To show my work, I would write the limit as x approaches 0 from the positive side of 1 minus the limit as x approaches 0 from the positive side of 4 over x squared. And this gives me something like 1 minus infinity. Now be a little wary. If we had infinity minus infinity, we couldn't have done this calculation. But since this exactly equals 1, and this limit is going to infinity, 1 minus infinity is the same thing as negative infinity. So we've just shown that on the right-hand side, this vertical asymptote is going down to negative infinity. We can do the same thing for on the left-hand side. Of course, you may have guessed that we'll use the left-hand limit. And here's what the work would look like. For the next example, we'll use a slightly different technique because there is no fraction here. So I can't just find the vertical asymptote by looking at the bottom. But I do recognize that the natural logarithm function has an asymptote. And actually, this natural logarithm has been shifted left 3 units. So if you think in your head what the graph looks like, this is the normal natural logarithm function. My natural logarithm has been shifted down 1 and left 3. So this intercept point goes down 1 and then left 3, which means the new vertical asymptote's right here at negative 3. and the function crosses through that point. Using this kind of logic, which I can do without a calculator, I can go ahead and identify that the vertical asymptote is at x equals -3. Next, we want to know what happens on the right and on the left. Well, one interesting thing is you already know from thinking about the graph that actually nothing happens on the left. On the left-hand side, the function doesn't exist because it's a logarithm. So we can start by just writing that on the left, the limit as x approaches -3 from the left-hand side of this function does not exist. The whole function doesn't exist even. Now we're wondering about on the right. So I set up my right-hand limit, the limit as x approaches -3 from the right, and this time I'm actually going to write the limit in. It's the natural logarithm of x plus 3 minus 1. And we can evaluate this. So the first thing you should just notice is we can't plug in -3 because the natural logarithm is undefined. However, I can split my logarithm, and I'm going to split it into the limit as x approaches -3 from the right-hand side of ln of x plus 3 plus the limit as x approaches -3 from the positive side of 1. And the nice thing is that this second limit is the limit of a constant. We know what that is. Now, for the first limit, this is going to be a little tricky because we can't cancel out x at all, and we still can't plug in -3. So this is where we're going to pull out one of those old tricks. We're going to pull out u substitution. And I'm about to evaluate the second limit, but for the first limit, I'm going to say u equals x plus 3 so that I can substitute my variable. And if I change the variable in the limit, I have to change the variable at the bottom as well. So as x gets really close to -3 from the right-hand side, u is going to get really, really close to 0. And that's because think about what would happen if I plug in a -3 right there. And we'll still be getting close to 0 from the positive side. So down here on the next line, I can switch the variables for my limit, and I would end up with the limit as u approaches 0 of ln of u plus, and don't forget this, the 1 at the back. A lot of people are going to drop that by accident. Now this is great news. We know this limit. This is one of the limits you just memorized. The limit of the natural logarithm as u approaches 0 is -∞. And -∞ plus 1, well, that's -∞ too. So we've just proven that the asymptote is on the right. All right, now I'm going to cheat a little bit for the last one, but it's an interesting case, so think about it just for fun. This one's going to have a vertical asymptote anytime the bottom equals 0. In other words, anytime sine and cosine equal the same thing. So there's going to be a lot of asymptotes, but the easiest one would be pi over 2. Remember, on the unit circle, pi over 2 is where sine and cosine equal the same thing. Well, think about what happens as we get closer to pi over 2, but the angle is a little bit larger. So if we come this direction, well, in this part of the unit circle, sine is a little bit larger than cosine. So sine minus cosine is going to be a positive number. Now, it's going to be a positive infinity because we're talking about dividing 1 by a very, very small positive number. And then as we approach it from this side, if the angle's a little bit smaller than pi over 2, cosine's going to be larger. So this one's actually going to be -∞ because a smaller number by a slightly larger cosine is 1 divided by a slightly negative decimal. I know I didn't explain those fully. I want you to try some on your own. So think about these. When you press play, I'll show you the answers. Here's 1. Here's 2. And here's